All right. Well, hello and welcome to our Wednesday Wednesday edition of Chem 305. I almost said 400. It's Wednesday. Whoa. Sorry. I have I always have a monitor going so I can kind of see how it looks on YouTube, keep track of the lag, all that good stuff. But when I forget to mute my computer, then I hear the echo of my voice. It's always a little bit bewildering. So yeah, hello, good afternoon. We today will be polishing off chapter 5 and moving on to chapter 6, because 6 comes after 5. So let's go ahead and dive on in. I don't think I have any pieces of business. Nope, nothing comes to mind. Other than check out the daily mixtape. It is a meditation on death and evil. It's 4 songs. Kind of was the headspace I found myself in this morning. And if you're wondering why, it's because I was writing exam 2. So I know everybody's mind is kind of on the first exam, which drops on Friday, but my head is already engaging in writing number 2. So anyways, if you want an insight into a glimpse into my psyche, where it was at, check out our daily mixtape. There's some cool beans on there. All right. Enough with the music commercials. Let's actually start talking about some chemistry. So we have one last thing to cover in chapter 5. Yesterday, we hit the gauntlet of molecular geometries. And the last thing we have to discuss, and this is something that we'll circle back to a little bit later in the summer session, but it gets introduced here in chapter 5, is the idea of polarity. All right. Now, at this moment in time, as far as we know, there's 2 types of bonds, right? We've got 2 types of bonds. We have ionic bonds, and we have covalent bonds. Let me scoot my covalent over. This is one advantage to lecturing in Photoshop instead of on a blackboard, and that is here I have access to the lasso tool. All right, so we have these 2 kinds of bonds, right? We know we can form ionic compounds. We know we can form covalent compounds. We know that for ionic bonds, that electrons are taken, right? The nonmetal punks the metal for its electrons. We know that in covalent bonds, however, electrons are shared. Electrons are taken. All right, so we know the difference between these 2 types of compounds, ionic and covalent. We know the difference between these 2 types of bonds. We even know how these form. We talked about how ionic bonds, we showed how the electrons are taken. With covalent bonds, we showed how they're shared, right, to satisfy the octet rule. But we have not yet discussed what causes an ionic bond to form as opposed to a covalent bond. All right, you may have noticed it has something to do with nonmetals and metals, right? We saw all of our covalent bonds were nonmetals pairing up, whereas our ionic bonds were metals together with nonmetals. You may have noticed that. And that has something to do with the answer, but the reason why, what causes an ionic bond to form over a covalent bond has to do with something called electronegativity. Electronegativity may be the longest word in the English language, I'm not sure. It always feels like it takes forever to write it out. Now, electronegativity is a measure. A measure of what? A measure of, quote unquote, how bad an atom wants to gain electrons. All right? It's a measure of how badly an atom wants to gain electrons. And if we look at our periodic table, all right, electronegativity actually trends along the periodic table like so. As you move from the left side of the periodic table to the right side, your electronegativity increases. So the further to the right you are on the periodic table, the more electronegative you are. And as you move from the bottom of the periodic table to the top of the periodic table, electronegativity of an element also increases. All right? It should come as no surprise then that the most electronegative elements tend to be closest to the noble gases, right? This should come as no surprise because we know that all these elements want to have a noble gas configuration. So the closer they are to attaining that, the harder they're going to want them, right? So we see the most electronegative up in here. Right, these are the most. Electronegative are up in this corner. The least are going to be down in this corner. All right, these are the least electronegative. The most are up and to the right. The least are left and to the bottom. All right. Now, the reason why all of this is important is it is the difference in electronegativity between two elements that determines whether or not a bond is covalent or ionic. All right. And let me say that again. The difference in electronegativity which from this point on, I'm going to write the difference in electronegativity like this. I'm going to write a delta, which is a symbol for change in En. All right, that will symbolize the difference in electronegativity between two elements determines whether a bond will be ionic or covalent. All right, the difference between the electronegativities of two elements determines what type of bond they'll end up with and whether that bond will be ionic or covalent. Now, let's hang on. Okay, good. I was just making sure the video feed didn't freeze. So, what exactly do I mean by this? And here's what I mean. All right. So, for example, let's look at a bond between so here, let's look at a bond between carbon and hydrogen. All right, carbon has an electronegativity of, so here, carbon has an electronegativity of 2.5. Hydrogen has an electronegativity of 2.1. And anytime the difference, all right, and when we say the difference in electronegativity, we always mean you subtract one from the other. Whenever the difference in electronegativity between two elements is 4.0 or less, that bond will be covalent. All right, so if, actually, hang on, I'm going to, yes, okay, Parthana, that is an excellent question. She asked, will the electronegativities be given? Absolutely. These are not things you have to memorize. And actually, I want to restructure this page just a little bit. All right, so let's look at bond type. Totally. Compare it to the difference in electronegativities. So when your bond type is covalent, your bond type will be covalent when the difference in electronegativity is 0.4 or less. All right. So if your difference in electronegativity is 0.4 or less, that means your bond is covalent. Here, when you compare carbon and hydrogen, because their difference in electronegativity is 0.4, the type of bond they're going to make is a covalent bond. All right. Now, what about ionic bonds? All right. For ionic bonds, the difference in electronegativity for a bond to be ionic is going to be, you'll have to have a difference of electronegativity of 2.1 or more. All right. So, for example, if we compare the electronegativities of fluorine and lithium, all right, here, the electronegativity for fluorine is 4.0. The electronegativity for lithium is 1.0. So the difference in electronegativity between fluorine and lithium is 4.0 minus 1.0, which equals 3.0. That difference in electronegativity is greater than 2.1, so these two elements form an ionic bond. All right? Excellent question, Parthana. So you may notice 0.4 or less, covalent, 2.1 or higher, ionic. What happens in this no man's land from 0.5 to 2.0? All right, they're not covalent, they're not ionic. What are they? They are a special kind of bond called polar covalent. Polar covalent bonds. They exist in this no man's land between ionic bonds and covalent bonds. Now, so what does that mean? Well, that means it's a little bit of both. We know that ionic bonds, electrons are just taken, right? They're greedy. The elements just rip the electrons away from other elements, take them for themselves. We know covalent, super chill, super hippie, right? The electrons are shared, everyone's happy. Well, polar covalent is this weird mix of the two. It's still covalent, so the electrons are still shared, but they're not shared evenly. There's a little bit of that selfishness that we see in ionic bonds that taints the polar covalent bond. All right. An example of a polar covalent bond, for example, would be the bond that forms between oxygen and hydrogen. All right. Oxygen's electronegativity is 3.5. Hydrogen's electronegativity, oh here, let me color code this. .5, hydrogen is 2.1, so here the difference is 3.5 minus 2.1. This comes out to be 1.4, and this is definitely a polar covalent bond. We can just call it polar for short. Now, what that means is in the oxygen and hydrogen bond, the electrons are still being shared, but they're shared unevenly. So with polar covalent bonds, electrons are unevenly shared because the electrons spend more time around the more electronegative nucleus. Prathana. Oops. Okay. All right. Now, consider let's consider a molecule of water. All right. We know that oxygen is more electronegative than hydrogen, as we saw, and so as a result, it pulls harder on the electrons in that bond with hydrogen. The electrons are more attracted to oxygen than they are to hydrogen, and so they spend more time around oxygen. These arrows that I'm drawing are called dipoles, and they indicate an uneven electron distribution, all right? So with a dipole arrow, you'll notice that there's two sides. There's the arrowhead, and then there's a little tail with the hatch mark through it. This part shows the, or let me give myself a little more room. This here shows the negative end of a bond, and this part right here shows the positive. Shows the positive end. All right. So what these arrows are saying is the electrons are pulled harder towards oxygen because it's more electronegative, and as a result, the electrons spend more time there. All right. This is like when there's that house in the neighborhood that all the neighborhood kids want to go and play at because they have the PS5 already. It's not even released yet, but all the kids want to play the PS5, so they're all over there at that house. And so they still live at the other houses, right? It's not like all the kids live at that one house, but they spend more time playing at those kids' house because they have the cooler thing than any of the other homes, right? Or in summertime, it's like the house with the pool. What this creates is a partial negative charge, not a full-blown negative ionic charge, right? Because the electrons aren't taken. This bond is still covalent, but it's partially negative on oxygen, and it creates partial positive charges on hydrogen. All right? And so this right here represents a partial negative charge all right, that's the Greek symbol delta with a minus sign, and then the delta plus indicates a partial positive charge. And these are created, this partial negative and these partial positives are created by the polar bonds between oxygen and hydrogen by the difference, or differences, in electronegativity. All right? So, polar bonds created by electronegativity differences between 0.5 and 2, all right? Anywhere in that range, the bond will be polar. And that uneven sharing of electrons creates partial negatives and partial positives, all right? Now, polar bonds in a molecule can give rise to a molecular property we call polarity, all right? That's ugly. Let's talk about molecular polarity. So we say that a molecule is said to be polar so a molecule is polar if two conditions are met. All right. Two conditions have to be met if a molecule is to be considered polar. The first is your molecule has to have polar bonds. All right. If it does not have polar bonds, it's automatically not polar. All right. But having polar bonds isn't enough to make a molecule polar. The second thing that the molecule needs to have in order to be polar, or needs to not have, is there cannot be identical groups, or actually, it's a horrible way to say this. Let me put it this way. The arrangement of groups around the central atom must be asymmetric. We'll talk about what that means in a second. In other words, symmetry cancels polarity. All right. So what are we talking about? When we talk about symmetry, right here, what we mean is we're talking about the same group at every position around the central atom. All right. Now, I know these are a lot of words. They're not going to make sense until we start doing examples. So let's go ahead and start assessing, using these rules, applying these rules to assess whether or not a molecule is polar or nonpolar. Okay? So let's do some examples. Keep these in mind. Maybe open a second screen, pause the video here so you can look at this while I do these next few examples. But let's start applying it, and that's really going to illustrate what this means. Okay, so let's do some examples. Let's determine if each molecule is polar. All right, determine if each molecule is polar. We're looking for two things, right? Whenever you see that word polar, we need two things. We need polar bonds and we need asymmetry. Yes, Brianna, exactly. That is exactly it. And you'll see. So actually, that's my first example. So let's look at H2O. Yeah, totally. So, first thing to check, do we have polar bonds? All right, that's the first thing to look at. Oxygen has an electronegativity of 3.5. Hydrogen has an electronegativity of 2.1. So the difference here in electronegativity, 1.4 as we calculated on the previous slide. So we have polar bonds. All right. Number one checks out. Shoot. Hang on 1 second. All right, we're good with number one. Number two, are we asymmetric? Here, you have to look at the electronic geometry. All right. If you look at the electronic geometry for oxygen, here, let's look at our electron groups. We have 2 atoms, 2 lone pairs. So we have 4 electron groups. All right? A compound with 4 electron groups, a central atom that has 4 electron groups, for this to be symmetric, we need 4 of the same thing, all right? But what are the groups around oxygen? Two H's and 2 lone pairs. Because these are not the same, because we're not, this is not 4 of the same thing, that means that this central atom that we're dealing with an asymmetric case, right? It has to be perfectly symmetric. You have to have 4 of the same thing for them to all cancel out. So because this is asymmetric, because 1 checks out and 2 checks out, that means that water is a polar molecule. All right, water is a polar molecule. Let's do another example. All right, let's look at carbon dioxide. All right, first, we want to know, is this thing polar? Carbon, well, actually, let's start with oxygen, has an electronegativity of 3.5. Carbon has an electronegativity of 2.5. So the difference here in electronegativity is 1.0. Remember, polar is anything from 0.5 to 2.0. So this is definitely polar. Now, let's look to see if this is symmetric. All right, if you look at carbon dioxide, if you draw out the Lewis structure, that looks like an E, that's weirding me out. if you look at the Lewis structure for carbon dioxide, it is a linear molecule. Right here we have linear. Linear molecules have 2 electron groups. And you'll notice we've got 2 electron groups, and there is an oxygen in both. In this molecule, both are oxygens, both groups are oxygens, which means this molecule is symmetric, which makes it nonpolar. All right, and the reason it's nonpolar, let's look at our dipoles. We know that the arrowheads are pointing towards oxygen, right? Because the electrons are pulled towards the oxygen, away from the central carbon. These dipoles cancel each other. All right? They're pulling in opposite directions, away from each other. So the one oxygen is trying to tug the electrons down closer to it. The other oxygen's pulling in the opposite direction, and it's like watching a tug-of-war match where the 2 people who are pulling on the rope have the same strength. Nothing's going to move, nothing's going to change. They cancel. Anytime you have the same group at every position around your central atom, you're going to be nonpolar, even if your bonds are polar. All right, so CO2 is a nonpolar molecule. All right, let's do a couple more. All right, let's assess the polarity of let's do, well, let's do CH3F. All right, now here we actually have, in this molecule, if you draw the Lewis structure, we have 2 different types of bonds to look at. We have to look at carbon, hydrogen, and carbon-fluorine bonds, right? Because we want to know, are any of these bonds polar? Carenza. So Carenza just asked a question, how do you identify the electron groups? So the number of electron groups, and this is from yesterday's lecture, so it's brand new, it's still fresh. The number of electron groups is equal to the number of atoms attached to the central atom plus the number of lone pairs on the central atom. So the number of electron groups is related to, determines the electronic geometry, and the number of electron groups is equal to the number of atoms attached to the central atom plus the number of lone pairs on the central atom. All right, so here we need to look at the electronegativity difference for hydrogen and carbon, which is 2.5 and 2.1, but we also need to look at the electronegativity difference for fluorine and carbon. All right, we've got 2 types of bonds that we need to analyze here. All right, and this is equal to, so first carbon and hydrogen have an electronegativity difference. Yes, exactly. That is exactly correct. The molecule that we're currently looking at has 4 electron groups because there's 4 atoms and 0 lone pairs around the central atom. The electronegativity difference for fluorine and carbon is 1.9. All right. Now, the difference between carbon and hydrogen, this is a nonpolar. Those bonds are nonpolar. They're just straight up covalent. Oops. But the electronegativity difference between, you are very welcome. The electronegativity difference between fluorine and carbon, totally polar, all right? And you'll remember, or you'll notice, Esther, it totally should. Good catch. The electronegativity difference for carbon is not 2.1, it's 2.5, which means our difference in electronegativity here will be 1.5. Still polar though. Fortunately, that does not change. So our carbon-fluorine bonds are polar. Now, to determine whether or not a molecule is polar, it doesn't say that all the bonds have to be polar. We just need to know, does it have polar bonds? And we do have one polar bond. So step number 1 checks out. Now, is this asymmetric? All right, let's check out our second criteria. So you'll notice that this molecule has a tetrahedral geometry, electronic geometry. It's tetrahedral, which means that it has 4 electron groups. All right, 4 electron groups. And you'll notice that we have 1, 2, 3 hydrogens, but then the 4th is different. It's fluorine. In order to be symmetric, you need the same thing on all 4 positions, but we don't. That means that we're dealing here with the asymmetric case, which means that this molecule is polar because it has polar bonds and it is not perfectly symmetric. Let's take one more example for a spin. Let's look at CF4. It's going to take me a little bit to dot in all of my lone pairs, but we got to be complete. All right, step number 1, do we have polar bonds? And we know that we do. We saw this in the last example. Fluorine is 4.0, carbon is 2.5. So our difference here is 1.5. We have polar bonds. All right, second, is this molecule symmetric? Because if it is, it doesn't matter if we have polar bonds, they cancel each other out. Our molecule's nonpolar. So here again, we're dealing with a tetrahedron. So here we have a tetrahedral geometry, which means that we have 4 electron groups. And when you look at the molecule, We have 1, 2, 3, 4, the same thing, the same atom at every position, which makes this symmetric. And if it's symmetric, our molecule is nonpolar. All right? That is the only thing that can cancel out polar bonds, is if you have the same type of bond at every position on your molecule. All right? That is how you determine whether or not a compound is polar or nonpolar. All right? Now, here's why this is important. All right? Whether or not a molecule is polar or nonpolar governs molecular attraction. What molecules are attracted to what other molecules? All right, molecular attraction is ruled by the following maxim. Like dissolves like is maybe something that you've heard. All right, so if you have an oil spill, you don't use water to scoop it up. You need something greasy, right? You need something like soap. And that all boils down to molecular attraction. You see, nonpolar molecules, nonpolar molecules are here. Sorry, I just need to scoot this down. Attract and dissolve other nonpolar molecules. They can attract and dissolve other nonpolar molecules, while polar molecules are able to attract and dissolve other polar molecules and ionic molecules. All right? And if you remember, and if you're going, well, wait a minute, if like dissolves like, I get why nonpolar molecules can dissolve other nonpolar molecules, but why can polar molecules dissolve ionic molecules? How does that work? All right? And here's why. Remember, if you're ionic, that means you're either positively charged or negatively charged, right? Polar molecules, if a molecule is polar, that means that it has a positive, partial positive, and a partial negative. So no matter what type of ion you're dealing with, there is a partial positive for the negative ions in your molecule, and there is a partial negative for the positive ions out there. So polar molecules can dissolve ionic compounds because polar molecules are partially charged. All right, so they can do both other polar molecules and ionic molecules. All right. Okay. This is the official end of chapter 5. Again, we'll be talking more about molecular attraction later in the summer session. But it gets introduced here because it's a natural outworking of molecular polarity. All right? Okay. So that brings us to the end of chapter 5 and the official start of chapter 6. Oops. All right, chapter 6 is super important chapter, possibly the most important chapter that we're going to cover this semester. And chapter 6 is about one thing and one thing only. It is a word that, if you have any chemistry in your background, it'll definitely ring a bell. And that word is stoichiometry. All right, stoichiometry. In this chapter, we see the return of math with its trusty sidekick, sig figs. And both of these topics are angry for being left out of the discourse for so long. They're going to come back with a vengeance. All right. Now, I'm not saying this to be scary, but I am saying it because if sig figs and algebra are things that you struggle with, you've got to take the bull by the horns here. You've got to confront the situation head on, because it's going to be nothing but math and sig figs for a while now. All right. This is usually the moment in the class where things quote unquote get hard. Most students find this to be the moment where the class takes a leap and becomes more challenging. I'm not saying that it's been easy so far, but it tends to get harder at this point. All right. So there's our warning. There's our caveat emptor. Let's start actually diving into it rather than talking about how hard it is going to be. Let's start talking about what it is. All right, and the most important concept in quantity that we will deal with this chapter is called the mole. All right, and I'm not talking about a small, furry, burrowing mammal with diminished eyesight. Though, if you're looking for a good time, Google star-nosed mole. Google image search star-nosed mole. They're weird. It looks like a mole was like jamming down the freeway at like 120 miles per hour and hit the back of an octopus, and it got stuck onto its nose. It's really, really gnarly. Give it a search. You'll love it. But in chemistry, a mole is something else. All right, and the mole, is a quantity, and it's a quantity similar to one pair. All right. If I asked you how many things are in a pair, you would tell me that one pair, hopefully, is two things, right? If I asked you, a mole is similar to a pair. A mole is similar to 1 dozen, right? If I asked you how many things are in a dozen, you would tell me 12 things, unless you were a baker, right? A baker's dozen is 13 things. Yeah, it does look so weird. The star-nosed mole. Now, a mole A mole is like a pair, it's like a dozen, it's just a number of things. All right, that's all it is. The only difference is the scale. 1 mole is a lot of things. 1 mole is 6.022 times 10 to the 23rd things. That's all it is. All right. It has this number of things has a special name. It is called Avogadro's number. All right, Avogadro's number. It's super important. We're going to learn it. We're going to learn it a lot. We're going to use it a lot in this chapter. All right, and it basically just allows you to convert back and forth between different quantities. Right. It gives us the unit conversion. 6.022 times 10 to the 23rd things, right? Things could be anything like atoms, ions, molecules per mole. There we go, Avogadro's number. That's why I'm using green to underline Avogadro's number. Now, why are moles so important? Now that we know what they are, why are they so important? Well, atoms are small. I don't know if you know this. Atoms are small, and so when we deal with a quantity of atoms, we're not going to be dealing with handfuls like 6 or 100 or even like millions. We deal with like there is a insane amount of atoms inside any sample of matter. As a result, we need something that's a giant quantity. We couldn't talk about dozens of atoms. We need to talk about moles of atoms. All right. The second reason has to do with the atomic masses on the periodic table. All right. If you look up the atomic mass for carbon, it's 12.01, and the number on the periodic table is unitless. Now, you know that the units for atomic mass are AMU, which are atomic mass units. All right, that's what we've been dealing with so far. But the reason why units are not included is because those numbers, those atomic masses, also tell you the number of grams of that element in a 1 mole sample. So if you have 1 mole of carbon, it will have a mass, that sample will have a mass of 12.01 grams. All right? Our atomic masses can also be written with units of grams per mole. All right? Grams per mole and AMU are the same thing, and we use this one over and over and over again. All right? With this knowledge, we can now solve problems like the following. All right, problems like the following. How many atoms are in a 5.00 gram sample of carbon? Yeah, this is the big reveal. You're like, he wasn't transporting himself, he was murdering his clones the entire time. It's a plot twist for a movie I've seen. You should go see it too, but now I don't want to say what the movie is because I don't want to spoil it, because I did. But if you don't know the name, you won't know that that's what's going on. Okay, so anyways, how many atoms are in a 5-gram sample of carbon? Here's how you handle it. All right? This is just a new type of unit conversion problem. You have 5 grams of carbon. All right? Now, the key to solving this is the atomic mass of carbon. You were in that movie? Wait, for real? I'm gonna freak out if that's for real. It's one of my all-time favorite movies. We can use the atomic mass as a unit conversion because we know that 1 mole of carbon has a mass of 12.01 grams. Dude, get out. Okay. That is so stinking rad. I am fangirling hard because it's an awesome movie. That is so cool. I'm gonna have to go rewatch it, and I'll be like, one of my students is in here. Try to find you. Okay. That's for later. Let's finish this problem. Okay. So how many atoms are in 5 grams? A 5-gram sample of carbon. We can use the atomic mass to convert from grams of carbon to moles. And then we can use Avogadro's number to convert from moles of carbon to atoms, because 1 mole of carbon, 1 mole is just 6.022 times 10 to the 23rd things, and those things can be anything. In this case, in this problem, it's atoms of carbon. Oh man. Yeah, totally. Okay. Now, if you look at where we position moles of carbon cancel moles of carbon, grams of carbon cancel grams of carbon, the only unit left is atoms, right? Atoms of carbon. And so that is the unit we're after. So now we can calculate, we can crunch our numbers, right? We take, I'm opening up my calculator, we take 5.00, divide by 12.01, and then multiply by 6.022 times 10 to the 23rd. The value that my calculator is giving me is 2.50707744. All right. When I look at my significant figures, my initial mass has 3, Avogadro's number has 4, and my atomic mass has 4. So we got to roll with the fewest, right? We're doing multiplication. So I count up my first 3 sig figs, round to that place. That 7 will round up. So this will. Hang on. I forgot a huge part of this number, right? It's 2.5077 or 2.50707744 times 10 to the 23rd, right? Drastically different number without it. After we round, it'll be 2.51 times 10 to the 23rd, and then our units are atoms of carbon. All right, so the atomic mass and Avogadro's number allows us to take the mass of a sample of atoms and determine how many atoms are actually in that sample. We can't count atoms with our eyes, but we can use these two unit conversions and a mass to calculate how many atoms are in a sample. Conversely, we could take this and move in the opposite direction, right? I could give you a number of atoms, 4.16 times 10 to the 24th atoms of oxygen, and I could ask you what the mass is in grams. All right, I could say you have a sample containing 4.16 times 10 to the 24th atoms of oxygen. What mass in grams does this? That looks like it's mass in. Let me work on my spacing a little better. I could ask you what is the mass here. And again, this is a unit conversion problem that's just moving in the opposite direction. So we have 4.16 times 10 to the 24th atoms of oxygen. And to convert from atoms to moles, we need Avogadro's number, right? 6.022 times 10 to the 23rd atoms of oxygen in the denominator is 1 mole of oxygen. So now atoms of oxygen cancel. Susan, the 10 to the 23 is right here for Avogadro's number. Yeah, totally. But another sample could be any size. But Avogadro's number is always 10 to the 23. Next, we can convert from moles of oxygen to grams using the atomic mass. All right, here moles of oxygen will cancel moles of oxygen, leaving us with grams, which is what we're trying to find. Now that grams, the unit we're after, is the only one remaining, we get to crunch our numbers. So 4.16 times 10 to the 24th divided by 6.022 times 10 to the 23rd times 16 gives us, let's see, my calculator is giving me a value that is 110.528.064. All right, sig figs wise, I can only keep 3, right? Avogadro's number has 4, my atomic mass has 4, so I'm limited by my initial quantity of atoms. You count off your first 3, that 5 will round up. So the answer is 111 grams of oxygen atoms. All right, a sample with 4.16 times 10 to the 24th atoms of oxygen will have a mass of 111 grams. All right, so I think this is a good place to park. For today, we will pick up tomorrow with Chapter 6. We'll be doing more calculations. We'll introduce balancing chemical equations, which will become bread and butter for us in the future. But I think we're going to go ahead and pause it there. Dude, thanks to everybody for participating. Special thanks to Susan for being in the Prestige. Go watch that tonight if you've never seen it, because it is awesome. Okay, excellent. Jen, I'm so glad to hear that. And that is going to be my approach. I'm just going to gradually take everything one step at a time. So hopefully it's not going to be overwhelming, because we're going to ease into this thing. Cool. Dudes, thanks for showing up on a Wednesday, and I will catch you all tomorrow in class. Later.